In this segment, we're going to be talking about solving one-step algebra questions with using multiplication and division as our operations. And again, just like the last segment, if we're having an equation, the equal sign produces a left side and a right side, and we're going to use our teeter-totter here that I've drawn to represent the balance that's going to occur. And whatever you do one side, you have to do to the other side. Now, when we're doing multiplication and division with just single terms, when you do it to a whole side, it's not any different than when you're doing adding and subtracting. However, when you have multiple terms, doing something to a whole side is problematic. Now, this segment, we're not going to really see much of that, but we will see it in future segments. So it's important to remember that we're doing things to an entire side. So here's our first question, 3x equals 6. So that means I have 3 sets of x's, or 3 times x. Sometimes it's better to write them in brackets, so I can do that. Either way is acceptable. And so what that means is I have 3 x's on this side, 1, 2, 3. And on the other side, I have 6 ones. So it might look something like that. What we're trying to ask is, what is the value of 1x? We've got 3 x's. We want to find out what 1x is. So if I rearrange them so it looks a little bit more like this, then I'll be able to see a little bit better as to what 1x would look like. So this 1x is worth 2. This 1x is worth 2, and this 1x is worth 2. So what we want to do is we want to show somehow mathematically that instead of knowing what 3 x's are, we want to know what each and every 1x is equal to. And we have to divide it into 3 equal pieces because I have 3 x's. So if I was to do it physically, I might do something like this and separate them into groups that I could literally move them and separate them into physical pieces into 3 separate groups, and so that I could see what any one of these x's would look like. So this x is equal to 2, this x is equal to 2, and this x is equal to 2. And I physically move them. Mathematically, how do we show that with work? The way I like to describe it to students is if I drew a line between each of these, I've now separated them into 3 separate groups. So by drawing a line or my division symbol, I can show that I've divided it into 3 separate groups, so my work would look like this. And my line, which I call my division line, but it could also be thought of as this blue separation line, 3x divided into 3 separate pieces, so I show that dividing by 3 would end up producing 1x is equal to 2. Now, some people don't like writing the 1x. We don't have to write 1x. We can just say x is equal to 2. And that's how I would show that work, showing the separation into 3 separate groups. For this next question, I want to review and just make sure that if that is going to be my x, I've indicated that this is going to be 1/2 x because it takes 2 of these to make a whole x. So this is what I'm going to be using for my 1/2 x. Now 1/2 x can also mean the same thing as x over 2. And so it's important for students to see that 1/2 times x is the exact same thing as x divided by 2. 1 times x is 1x or x, and I still have my division by 2. Dividing by 2 and multiplying by 1/2, we've talked about this when we talked about our fractions. If I'm multiplying by something smaller than 1, I'm going to get fewer of them, and if I divide by something bigger than 1, I'm going to get fewer of them. So these are both equivalent pieces. So it makes sense for students to understand both of these work and mean the same thing. Once we've covered that, we can do a question something like this. So my question is, x divided by 2 equals 4, which we just got finished saying would be the same thing as saying 1/2 x equals 4. So here's my diagram for that. What we're looking for is we want to find out what x is. We want to find out what one of these is equal to. And we only know what half of one of these is equal to. We know half is equal to 4. So how much would a full one be? Well, we can see that we're going to need another one to make a full. So if each one of these is worth 4, we're going to need to add 4 more to this side. And so now we can see if a half is equal to 4, then a full must be equal to 8. So there we are visually what that's going to look like. We started off with our question 1/2 was equal to 4. I need a full, so I need to double it. And so therefore I need to have 2 rows of those. So my full x now is going to be equal to 8. Now mathematically, how do we go about showing that? So the work that we have to do here is we have to somehow get rid of divide by 2. Well, the opposite operation of dividing by 2 is multiplying by 2. And that's what we ended up doing here. Instead of having 1/2 x, we now have 2 1/2 x's to make a full. So we showed that we had to double it somehow. So if we show that we double it by multiplying it by 2, that's how we would write it mathematically or symbolically. Now lots of students will just write the times it by 2 down here because it's the 2 that they were multiplying. And I really want to make sure that we clarify that we don't do that. The reason I don't want to do that is because now if I go 2 times 2, I'm really going to get a 4 down on the bottom, and that's not what I'm getting. I'm getting a 1. So what I'm doing, I can think of it over here, is if I'm multiplying 1/2 by 2, that's going to allow me to do some canceling. 1/2 times 2 gives me 1x, and that's why we want to make sure that we put the times 2 up on the top. So over here, when we're doing the times 2, we want to make sure that we put it on the top half of the line. And this is really critical, especially when we have more complicated numerators and denominators, because lots of students will get confused with this. We want to be able to do this crossing out piece that we just did over there, and so we want to make sure that it's on top. Since we doubled the 1/2 x, we have to double the other side. So I'm just going to take this 2, I'm going to duplicate it, and whatever we did to one side, we have to do to the other side. And so therefore, our answer now is going to be x equals 8. And there's the work we would show no matter which technique we were using, with the multiply by 2 on the top, so it cancels, leaves me with x equaling, and I did the same thing to both sides, 8. There's the canceling, x equaling 8 on both sides. This next question I'm going to include here because it's a one-step action, or it could be multiple steps depending on how you do it. That's really critical for students to be able to understand how to do. And it involves having our negative values with our x. So if my question is negative x equals 2, we don't want to know what negative x is equal to. We always want to know what positive x is going to equal to. So students very quickly will say, well, if I just flip this from a red into a green, then I just flip these ones from a green into a red. And so my answer is a positive x would have to equal negative 2 because it's just the opposite thing. I don't want to know what a negative x, I want to know what a positive x is. So I flip this one, so I flip that one. And so with the tiles, it's quite simple. It's just a matter of flipping the tile from one color to the other tile, or from one color to the other color. But mathematically, how do we do that? How do you show that we just flip them? Now, in some cases, I have students who just write the word. They just go right, and they just write in there, and they write in the word, or they print in, and they flipped it, and they just write it in with a word, because mathematically they're not sure how to show that. To me, that's okay. And so the next statement would then be positive x is equal to negative 2. And it would look like that. You don't have to write the positive x, and so I'm perfectly okay with that. Mathematically, however, we want to show how we can do that and what the work would look like, so it would look something like this. Since we're saying we're going to flip it over, we're going to do the opposite thing, I can multiply by the opposite. So I have a negative 1x, so if I multiply it by a negative 1, multiplying by a negative 1 changes the sign of something, and so I can multiply it by negative 1. That's the work that I would show to show that I would flip it from a negative to a positive. Whatever I do to one side, I have to do to the other side, and then I would end up getting my positive x is equal to negative 2. The other way of doing that would be, instead of doing a multiply by a negative 1, I could also, if the student feels more comfortable, divide by a negative 1. A negative divided by a negative gives me a positive. So if I divide by negative 1, my sign is going to change. The number's not, because dividing by 1s don't change anything. But I'm dividing by a negative 1, so my sign changes to a positive x. And if I do one thing to one side, I have to do the same thing to the other. Divide that side by negative 2, by negative 1. So 2 divided by negative 1 is negative 2. So I can either show it by multiplying by a negative 1 to both sides, or dividing by negative 1 on both sides. That's the mathematical work to show that flipping of the color. So now we're going to do a question, negative 2x is equal to 4, and this is going to show that working with the manipulatives is sometimes a little bit more complicated than working with it symbolically, but it's important that students understand where the pieces come from. So the first thing I might want to do is, if I have two x's, I might want to just split them apart. And so therefore I know that any one negative x is equal to positive 2. So mathematically, my work would look like this. I'm going to draw my line, which indicates I'm splitting it into two different pieces. There's my piece that I'm splitting, so there's my line right there that's splitting. So I divide both sides by 2, and I get negative x is equal to 2, which is what my diagram shows. Each one of these negative x's is equal to positive 2. But I don't want to know what negative x is, I want to know what positive x is. So just as we just got finished talking about, there's two ways. I can either divide by a negative 1 or multiply by a negative 1 to solve that. So I'm going to multiply by a negative 1. And there it is there. Now I have a positive x is equal to negative 2. And in my pictures, what does that mean? If I multiply by a negative 1, that means I'm going to change the colors. So I'm going to change the colors in my diagram. And whatever I did to one side, I did to the other. So my reds are now greens, and my greens are now reds. And it shows that x, positive x, is equal to negative 2. And there it is right there. Here's my original question again. Some students don't like working with the negatives, and so what they could do is they could get rid of my negative 2x by adding a positive 2x to both sides. And that's going to produce a 0 pair here and a 0 pair here. So mathematically, what's that going to look like? Would be this. I have 0 now on the left-hand side and 4 plus 2x on my right-hand side. At least now my x's are the color that I want. So I'm going to take these and I'm just going to eliminate them because I've done that now. So my question looks like this. So now I can move my 4 greens over to the other side. And again, we can do that by adding 0 pairs. So I'd have to add 4 reds to make 4 0 pairs. And I have to do the same thing to the other side. And so here's my 0 pairs. And so they're basically gone. Whatever I did to one side, I have to do to the other. So mathematically, what do I have now? Would be this. Negative 4 is equal to 2x. I now don't have to worry about my negative x's anymore. I have 2 x's, so I'm going to split them. And I can remove my 0 pairs. So I've removed my 0 pairs. I've split my x's into 2 sections because I want to know what one x is going to equal to. My work shows me there's my line, which is the same as my blue line here that's dividing them. And so now I get negative 4 divided by 2 is equal to 2x divided by 2. My 2's are going to be able to cancel. Negative 4 divided by 2 is negative 2, so my work would look like this. Negative 2 equals 1x, or x. And so that's the same answer we had, just using it in a different way. Again, it's important for students to understand that there's more than one way to get to an answer, and they're all acceptable. Some take more steps than the others, so they may not be the most efficient way. And our goal is to try to find an efficient way. But if their way makes more sense to them, they're going to work with that way, unless there's a timeline or a time crunch. And they may move to the more efficient technique on their own once they figure out and feel comfortable with the one that they're working with. And when students are comfortable with either of those techniques we've talked about, we can talk about the efficiencies of the symbolic technique. We want to be able to split them into 2 groups, and we want to be able to flip the colors. We can do that all in one step symbolically by dividing by a negative 2. This division allows me to do the dividing part into 2 separates. So that line there is my division line, which corresponds with that blue line. And instead of doing it one at a time, dividing each one by negative 1 to change their colors, we can do it all in one step. So this one step here symbolically allows us to do the split and the flip of the colors all in one step. And so concretely it would look like this, and symbolically it would look like this. So we've talked about one step moving with multiplying and dividing, with positives and negatives as well, to change the signs and the colors.